So we have discussed what is mean by ring. What is the definition of ring? Definition
So
of ring.
a ring is a non-empty set R, and the binary operation is addition and multiplication.
Two binary operations. Instead of one, we have two binary
Yes,
operations.
yeah,
Okay.
two
Yeah.
binary operation. And
Then
then we have discussed the conditions that it is abelian group under addition, then
what is
semi
mean by
group under
abelian group?
multiplication.
What is mean by abelian group?
Abelian group, it holds only commutative law, like AB is equal to BA.
Commutative law together with group properties.
Yes, and
So
you
all,
also gave us a homework that find examples of abelian
yes,
groups.
exactly. What about semi group?
What, sir?
Semi group. What is the meaning of semi group? It is abelian group under addition, and it
Yes.
is R is the semi group under multiplication. So tell me, what is mean by semi group?
Where
Semi group means
if A satisfies, means if any A or
any
any
set
set
A,
A satisfies a closed and associative property.
only close and associative properties there, then it is semi group. So we have discussed here that thing. Okay. So this is
Okay.
that four property together will use us a definition of group. Okay. And if any set A which is non-empty satisfying first property and second property, then that set A is called as the semi group. Okay, so we have an example here. Every group is semi group. Every group is semi group. But here n natural number with the plus is not a semi group. Not a group, but it is a semi group. Okay, it is not. Why it is not a group? Because identity element is not. Okay, that's all. And abelian group. Yes, tell me what is the example of abelian groups?
Sir, sir, can I tell?
Yes, please.
Z
Sir,
plus
Very good. Z plus. Any another example?
Q
sir,
plus
What?
Q plus Q
Q plus. Okay, Q plus. Any product group?
I plus
R
I
plus
plus
Okay. Any product operation? R star into dot. Any
sir,
finite?
n dot also. N dot.
N natural
Sorry.
number नहीं हो सकता because inverse does not exist. No. We have that four property together with associative commutativity. Okay.
Sir,
Yes.
sir, yesterday, when you gave the homework, I took one example for commutative property that when A plus B is equal to B plus A, for all AP belongs to I. So I tried with
Definitely.
A is equal to 19 and B is equal to minus 20. So it gets proved, and it's a abelian group.
Which you are talking about? Natural number.
Yesterday you gave homework, na? So for
Yes.
commutative property, it got proved. LHS is equal to HS.
Which group you are talking about?
Abelian only.
No. You are doing operation in which group? Tell me the group name.
Addition.
Addition is the binary operation, and what it said?
Set. I have just took numbers. A is equal to 19 and
that
B is
number you are
equal to
picking.
minus.
That number, whatever you are picking, from where you are picking, that set is important. No, that set we called as a group.
That's so. I have to tell set.
Which set?
No, I took that set. I is equal. First, I took. The question is that prove that I comma plus is an abelian group.
So what is I? Integers.
Yeah.
Yeah, it is.
Yes.
Obviously, it is simply we have z. Z is nothing but sometimes it is denoted by I also. It is abelian. No problem. I am talking about any finite group. Do you have which is abelian? Finite
group.
Okay. Instead of group, do you have any example which is non-abelian? Abelian, you have examples, no problem. Now I want an example for non-abelian. Any example? Yes. So think on that way, okay? If I will give you, then it is very easy for you. Find out, okay? It is some kind of matrices kind of thing. So you can think on that. Okay. Okay. So okay, I will directly tell you. This is nothing but what? Your matrices, which is non-singular. So non-singular matrices is denoted by, tell me, non-singular matrices is denoted by. So you can write down non-singular. What is mean by non-singular?
Not equal to 0.
Determinant is not equal to 0.
Yeah.
Yeah. So non-singular matrices, which is square also. Obviously, it is square. When I talk about non-singular, it must be square. Non-singular matrices with product, because it satisfies closed one. Because if you take any non-singular matrix, do the product with again non-singular matrix, whatever the result you are getting, which is also non-singular. Okay, because we know that determinant of A B is equal to determinant of A into determinant of B. Yes or no? Determinant property. So which is also non-singular. The second one, associativity is there because product is associative on numbers. So it is associative is there. Inverse, identity element, yes, we have. What is identity in the matrices? What is identity? It is I1, I2, I3. What is I1, I2, I3? It is nothing but the identity matrix. So I1 is nothing but only one. I2 is nothing but it is 2 by 2 matrices 1, 0, 0, 1. I3 is nothing but, what is I3? 3 by 3 matrices. So what is 3 by 3 matrices here?
1 0 0 0 1 0 0 0
Yes, 1 0 0 0 1 0 and 0
1 0
0
1.
1. Correct. Similarly, so this is identity matrix. So if you multiply this matrix to any matrix, you will get the same answer. So this is nothing but what you have identity, and it is non-singular. If determinant, if the matrix is non-singular, means what? Its inverse is exist. So this is the group. But whether in the matrices, matrix A into B is always equal to B into A in the matrices. Okay, you can check it out. A into B is not equal to B into A. Okay. So
Sir, this
therefore,
is which example for
see now, here I written what I written. Read it. Non-abelian group. It is a group, but
okay.
associate commutativity is not good. So this is what not commutative.
Okay.
It is group. But check it out. This is homework for you. Just check all properties and make a statement in the determinant. The product of the two matrices is not commutative. Okay. Okay. So this is what the example of non-abelian group. Okay. Where we are. So we revise the definition for you. The definition is ring. A non-empty set R is said to be ring if we have two binary operation. One is called as addition, one we call as a multiplication, and R is abelian group under addition, R is semi-group under multiplication, and both left and right distributive law holds in that particular set R. If that three properties are satisfied, then we say that whatever the R set is a ring with binary operation plus and 1. Okay, so let's have examples on that. Right down. Examples. So before going to start with the examples, write down the another definition. That definition is nothing but a commutative ring. So definition of commutative ring. Yes, tell me now what is mean by commutative ring. What do you think? Anyone? Write down. A ring R is said to be a commutative ring. If A dot B is equal to B dot A for all A and B belongs to ring. Okay, so tell me what is the difference between definition of ring and definition of commutative ring? Yes. Anyone?
Sir,
In the-
can you repeat the question?
What is the difference between the definition of ring and definition of commutative ring? Whether this whatever I written here, A into B is equal to B into A, that is nothing but the commutative law. Whether commutative law holds in ring.
Sir, for commutative, it doesn't hold associative law like we saw in ring. A dot B plus C is equal to
Exactly,
B
exactly.
plus C dot A. It doesn't come in commutative ring.
Yes, so we can write down the definition of ring is what? The definition of ring, A is abelian with respect to addition, and A or whatever AI instead of A R, we can say that R is semi-group with respect to multiplication. So semi-group means what? It satisfies only two properties. First one is closed one and associative one. Whether it satisfies commutative property here in the definition of ring? No. Suppose it also satisfies this property commutative, then that ring is called as commutative ring. Got it? Got it, everyone?
Okay.
Okay. So that is the extra property. Okay. Now also we have next a ring ring with unity. Next definition you can write down. Okay, so what do you think? What is the definition of ring with unity? So write down a ring R is right now with me, is said to be a ring with unity. It's said to be ring with unity if there exists an element we call as that element E, which is equal to 1, such that A into 1 is equal to 1 into A is equal to A for all A belongs to that. So it means what? The identity, the whatever we have semi group, if commutativity is bold, then we can say that it is commutative ring. And if identity element is also there with respect to product, then we call that ring with unity. Got it? Clean and clear? Everyone understand this
Sir,
example?
can you tell that after element E is equal to 1?
Such that it is
With
an
that
identity element.
identity,
Yeah, it's
okay,
an
okay.
identity. That's what we
Means
call as
A
a,
should come.
yeah, identity. If
Okay,
we have
understood.
identity with respect to product, then we call that ring with unity, and that unity is nothing but your identity.
Okay.
Okay, so initially we have ring. In ring, R is abelian group with respect to addition, R is semi group with respect to product, and R satisfied distributive one. Okay, together with that three properties, if R satisfy this property. Which one? A dot B into B dot A, commutative ring. So we call as this is commutative ring. Okay. And if R with unity, if R has identity element with respect to product, then R with unity. Now can someone tell me what is commutative ring with unity? What is commutative ring with unity? Commutative ring with unity. Here we have ring with unity. What mean by commutative ring with unity? Yes, anyone? Simple. It satisfies commutativity also, it satisfies ring also, and it has unity also. All that three properties. So first one it is ring, commutative means the second property, and unity means third property. That's it. Got it, everyone?
Sir, I'm here. You can you tell that once again? Commutative ring. No,
No.
sir. No, sorry. Commutative ring with unity.
Yes. What is mean by ring? Satisfy three properties. What is mean
Yes.
by commutative ring? That three property plus this property. What is mean
With
by
three properties, this remarks and definition.
remark means what? This is the definition of ring. No, what is definition of ring?
Okay.
R is abelian with respect to plus, R is semi-group with respect to product, and R satisfy distributed. That is what the definition of ring. No? And remark means definition
Yes.
of ring. So ring with this property. Commutativity is commutative ring. Ring with unity called as ring with unity. Now I
Okay.
want commutative ring with unity. So what we have? We have all these properties. Ring property is there, commutative is there, and unity is there. Got it?
Yes.
So this is what we have commutative ring. You can write that commutative ring with unity. Next one. So what we have? The ring plus commutative ring plus unity with respect to product. Okay, this is what the commutative ring with unity. Now let's see some examples. Example number 1. So first example. Z is the set of integers. First operation is plus, second operation is dot. Tell me whether it is ring, commutative ring, or commutative ring with unity. This is, tell me whether this is ring.
Yes, sir. It satisfies both
All three conditions.
add.
Yes.
Yes.
So first condition is what? Z plus is abelian group. Yes or no?
No, sir. I'm talking about this as Z plus comma dot.
What is the definition of ring? Can you repeat for me?
Okay. Empty set R is called as ring if binary operation, addition, and multiplication.
Hmm. Next.
And R is abelian group under addition.
So what I written here? R is nothing but my Z. So Z plus is abelian group
Yes.
with respect to plus. Yes or
Okay.
no? The
Okay.
second one. What is second property?
R dot should be a semi-group.
So whether it is semi-group means what? Z, we have to take the elements from Z and dot. So it is close and associative. So it is simply. But with respect to what? Product. So it is semi-group also. So this property is also satisfied. This property. What is third property?
Distributive.
What about distributive property? So which is there always, because we know that in Z, in this plus and dot are the distributive. Okay, we know that one. Already, I think for distributive law in the sets, we have done this. So distributive property is also done. So this is ring. Okay. Now, whether it is commutative ring, whether it is commutative ring,
Yes, sir.
why?
So any number multiplied in any order, it's the same product. It gives the same product.
Yes, so because it is also a commutative ring, since A dot B is equal to B dot A when A and B belongs to Z. We know that. If you take any two integers from Z, and if you do the product A into B and B into A, you will get the same product, any two numbers. Yes or no? So it is also a commutative ring. Now tell me whether it has a unity element. It has a unity element. Unity with respect to product. Yes or no? See here. See. Are it said to be a ring with unity if there exists an element 1 such that A into 1 is equal to 1 into A is equal to A. So whether such a element is exist. Whether such a element is exist here. In Z.
Just for product.
Yeah, just for product. Because it is abelian group. For abelian group, the group is also there and everything is there. For making this group, what we need? We need identity element and we need an inverse. But inverse is not there. We are not dealing with the inverse. We are just dealing with the identity element with respect to product. So you need to think whether in Z dot, whether identity element exists.
Yeah, yes, sir.
What is that?
One only.
One only. So also it is commutative ring with unity. Because commutative is hold above here, we just written here. So it is commutative ring with unity. What is that unity? It's E is equal to. So this is the ring with commutativity also there and unity is also there. So this is the ring with commutative ring with unity. Okay, got it? Got it, everyone?
Yes, sir.
Okay. Anyone?
So
Any?
means for a commutative ring with unity, all those conditions should be satisfied.
Not inverse is not there. See. What is your question? For
I asked that for a commutative ring with unity, the three
all three
conditions
conditions.
which
Yes,
you
yes,
wrote
yes.
means
First one is
for
ring.
abelian. Uh,
Ring one. That condition is always there. It is what I'm talking about. It is commutativity also, ring condition also, and unity condition.
okay.
Itself we have there everything.
No, these three conditions:
This
abelian
is the
group with respect
condition.
to
This
plus, semi group with respect to dot.
this is the condition for ring. This is the basic definition of ring. Okay, just see the definition of ring. What is definition of ring? It is and
Okay.
C. A non-empty
Okay.
set R is called as a ring with binary operation. This and multiplication which are defined in R, and these three conditions are satisfied. This is the definition of ring. If it is not a
Okay.
ring, then it is not commutative ring. It is not a ring with unity. Okay. So this is the definition
Yes.
of ring itself. Keep that in your mind.
Okay.
Okay.
Yes, sir.
Everyone got it? Other one? Any doubts? Anyone? Any doubts?
No, sir.
Okay. So now tell me the second example. The set of even integers with 0. 0 is also there. Huh? This is 0. Under addition and multiplication is a ring or not? Whether it is commutative ring with unity. Tell me, what do you think about that?
So it's a ring.
Okay, it is ring. Why?
So because even integers and plus binary operation, it's an Albanian group. Then then with the product, it's semi group, and it's also distributive.
So they are talking about even integers. Okay, even integers starting from 0 to 4. So I just called as that even integer is nothing but 2z plus.
Hmm.
2z plus with plus and dot. That is what they are asking. So my first condition, what is my first condition? Whether 2z plus is abelian group. Tell me, it is clearly closed because any two even numbers, if I will get the even number itself. Yes or no?
Yes, sir.
So closed is there. Associativity is there. What about identity here?
1.
No, 0, no. Plus
Sorry.
operation here.
Yeah, 0, 0, sorry.
0. And what about inverse?
Yeah, it's not present.
No. Problem is what? Instead of positive, they are not mentioning anything, no positive. They just mention a set of even integers.
Integers, yeah.
So negative is also there. Negative.
Yeah.
Whether they mention anything? No. So everything. So inverse is also there because -2 inverse is 2 or 2 inverse is -2 because identity is there. Here identity is there. So first one is satisfied. What is second one?
Semi group.
So
2z.
whether it is semi-group,
Yes.
simply it is semi-group because product is there. If you multiply any two numbers, so it is closed. And it is Z multiplication. So the multiplication is associative over Z and 2Z is the subset. So it is also there. Okay. So what about third one?
Is equal to 1.
No, first we say check whether distributivity is there.
Yes, yes.
Distributive is always there because we have plus and dot, which is always distributive over Z. Okay, so if it is distributive over Z, obviously it is distributive over its subset also, 2Z also. So distributive law is also there. With that, it is commutative ring. What is it by commutative?
A dot B is equal to B dot A.
In Z, A dot B is equal to B dot A. So it
Yes.
is commutative ring also there. Commutativity is good.
But it's not unity
Yes.
because 1 is not present in even integers.
Because identity element is not exist. See here, if you take any element, any even integer, and find out for that even integer, if you multiply by any number, you will get the same even integer. This is not the case. So unity not exist. So this ring is what? This ring is what?
It's just a commutative ring.
Yes,
Not-
it's just a commutative ring without unity.
Yeah.
Just the commutative ring. Okay, you can write down. Can you understand that?
So in
Yes.
we wrote that unity does not exist because the identity element is 1 and it does not
Yes.
belong integers.
Absolutely. Yeah. Now what happens? Suppose instead of Now next example you will understand that instead of giving this e is equal to 1, if I gave a different operation, modulo operation. What is mean by modulo operation? You know that. Modulo means what? If I consider ZP, Z7, so it has elements 0, 1, 2, 3, 4, 5, 6. And if I modulo operation is there, it means whenever I write down 8, so 8 is congruent to 1 because 7 congruent to 0, 8 congruent to 1, like that. Okay, so that time the identity element you need to think. Okay, so that is why what my next problem to write down. Everyone understand this without unity 1? This example, clean and clear?
Sir, commutative law unity does not exist because here e is not equal to 1.
Correct.
Or
Okay, identity element. Okay. Other than 1, do you have any other element which is the identity element which satisfy this condition? A dot E is equal to E dot A is equal to E.
no.
No, because that 2z contains or even integers with 0. So
Okay.
0 is there, 2 there, 4 there, 6 there. So what number you should multiply to 2 to get again 2? What is that E?
1.
1. But 1, whether 1 belongs to that set, 2z, whether it is
No.
even integer. No, that's why it is.
No.
Got it?
Okay, so if 1 would have been there, then it would have been
Yes.
commutative law unity.
Yeah, definitely. Commutative ring with unity ring. Okay? Got it?
Oh, yes.
Write down third one. Now, I just define Zm. Zm is nothing but my set, the set of integer modulo m. Now you know that. What is meant by set of integer modulo m? Under addition, and multiplication. When I talked about what are the operation on Zm, the modulo operation. Huh? Under multiplication, modulo m model is ring or commutative ring or what? Commutative ring with unity. That is what I have my question. So tell me, what do you think? For example, we will take, now we need to discuss that all things. No? So we will take any example. We will take Z4 first. Okay, Z4 with plus and with dot. That plus and dot plus is nothing but the modulo m operation. So tell me, first question. Z4 plus is abelian group. Yes or no? Z4 plus is abelian group. Tell me what are the elements we have in Z4?
0, 1, 2, 3.
2 and 3. Okay. So whether closed is there, we have solved such kind of problems. No? Abelian only group 1.
Yes, sir.
Okay. So whether it is group Z4 plus is a group.
Yeah.
Tell me elements. Tell me what is identity element then? What is identity element here?
0.
0. Tell me inverse of A. Inverse of 0.
0.
0 inverse. Okay. So 0 into 0 you will get 0. Okay. A into A inverse is equal to identity. What is inverse of 1? What is inverse of 1? So which element I should add here? Plus is there. Plus is there. Because we have taken plus as operation. So which number should I add here? So I will get 0. Yes.
5.
What? Which number? The 3. No, beta. What is 1 plus 3? What is 1 plus 3?
4,
4. And 4 is congruent to
0.
0. What about 2? Inverse of 2? 2 itself.
2. Yeah.
Because 2 plus 2 is 0. What is inverse of 3 again? Inverse of 3 is 1.
1.
Okay. We have done this. No? We have done
Yes.
this. No? Yes, sir. Please do the revision. So it is a commutative. Now tell me whether it is commutative or not. Easily, because if you add this element into this element or this element into this element, there is nothing changed because addition is there. And addition is commutative over Z, and Z4 is the subset. So obviously it is commutative. So it is abelian group. Okay, it is
Yes.
true. Got it, everyone? What about second? Z4 dot is
Semi-group.
semi-group. So whether it is semi-group,
Yes.
it is easy to show it is semi-group. Because closed one is there. If you do the product of any two numbers, 3 into 6, 6 again you are getting 6 mod 4. What is 6 mod 4?
2.
2. So 2 is also there. So it is closed. And associativity, for associativity, the
Yeah.
plus is associative over Z and Z4 is the subset. Therefore, it is associative over Z4. So it is semi-group. So it is ring. First, it is ring. Everyone understand whether it is ring or not? So it is ring is there. Whether it is commutative ring, whether it is commutative ring. For commutativity, what we want?
A dot B, B dot A.
A dot B is equal to B dot A. Whether it is true here?
Yeah.
Obviously. So this is true for all A and B belongs to Z4. Okay. So it is now commutative ring. So what is next? Identity. Whether identity element exists in Z4. Here whether identity element is exist. With respect to product. So what you want 0 into E is equal to 0, 1 into E is equal to 1, 2 into E you want 1, sorry, 2 into 2 is 2, and 3 into E you want 3. So what is that E here? What is that E? Put E is equal to 1, what happened? Whether all that 4 equations satisfied?
Yes, sir.
So identity element is also there with respect to product. Even if it is a modular product, the product is what? 1 into E, 0 into 1, I am getting 0. 1 into 1, I am getting 1. 2 into 1, I am getting 2. So this is what the definition of unity. So E is equal to 1. So this is what? Commutative
Ring with unity.
ring with unity. Okay, clean and clear. So whenever you have a question in assignment, or whenever you have a question in your examination, so that time you need to show that all properties are that properties. I have mentioned here like these properties, no? Abelian group, you need to show that it is closed, it is associative. You need to write down one or two statements. You need to draw a table also. Okay, so we have done, that's why I given you this important one. You need to draw a table for both because it is finite. Got it? Everyone know this about rings? Can I give you next one? Okay. Write down next one. Please write down this. Anyone any doubts up to this? Any doubts, anyone?
No, sir.
Okay. So now write down next one. Or subring. So we have just definition and definitions here for the subring and examples. So, what is the definition of subgroup? What is the definition of subgroup? Anyone? Definition of subgroup? Subgroup definition in last lecture we discussed that.
Yeah, it should be
Mhm.
subset of the group
Very good.
in itself.
And
It should be a group in itself.
with respect to the same operation that we have on group.
Group, yes.
Okay. So same thing, the same definition will work here. So you can write down a subset. A subset we can say.
This definition of subring.
Subring. That's why I'm writing here. No definition of subring.
Okay.
A subset R. So we can suppose R is a subset of my ring S. Okay, where what we have S1 plus dot is a ring. Is a ring. It's called subring. So we have one ring, okay, a big ring, okay, and which is a subset of some S set, okay, and S1 is a ring. It's called a subring of S. It's called as subring of S. Okay. With respect to subring of S, if that R plus dot is a ring with operation plus and dot. So you can take a subset of S. S is a set of rings. Okay. So you can take any ring. So in simple language, that is, if R plus dot is ring, then S is subring if number one, S is subset of R, and second one, S plus dot is a ring. Like that only. Got it? So suppose we have one ring and we wanted to show that its subset, non-empty subset, is a ring, or is a subring. If what you wanted to show that S is a subset of R, so it should be a non-empty subset of R, and it itself a ring with the same binary operation. See here, whatever the operation we have used the same operation there. Same operation there. So it is subset. Got it? Got it? Any example that comes in your mind? Any example? Yes. Any example? Suppose I have R plus dot is ring. So number one, tell me whether integer plus dot is subring of R.
Yes, it is a subring of R.
See what I want, whether Z is a subset of R.
Yes.
Okay. So Z plus is abelian group.
Hmm.
Z dot is semi group.
Hmm.
Distributive law holds. Then it is
Yes.
subring. So this is correct. If I take Zn plus and dot, whether it is subring.
Yes, sir.
It is not.
Why?
Why? Because here whatever I am using operation, these are the modulo operation. In the group also we have given same example. This operation is different. It is a subset, we agree. It itself free, we also agree. But operation is different. Whatever the operation we have defined here, that plus operation on R or dot operation on R. Here I can take any two numbers and do the usual addition. But here it is not a usual addition. If I take m and m plus 1 or m into m minus 1, so I am getting not answer that m, I am getting something different. Like, are you getting what I am trying to say?
Yes, sir.
Operation is different. So it is not. Okay. So please see that the definition very carefully. You are requested with the same operation. Okay. Now the third one.
Sir, can you
What? You are not audible.
show
Yes.
the definition of these are only the examples?
Is the definition.
Okay.
So you can take now 2z. 2z means set of integers, even integers. Whether it is a subring of R. Subring of Z I am talking about. Okay. Tell me whether it is subring of Z. What is Z? Z plus N. Tell me whether it is subring.
Yes.
No. Tell me what is identity element here in 2Z with respect to plus. If 0 is there,
Yeah.
if 0 is there, then it is. And we have 0 here, correct? We have 0 there. So it is it. Because we have directly take Z. Set of
Yes.
all integers with 0. So it is sub.
It is.
Sub. Okay. It is also subring. You can find many more examples like that. Okay. So this is what we have the examples of subring. Everyone understand that? Clean and clear?
Sir, can you tell why second is not
Operation
subring
is
first?
different. Operation is different. Whatever here plus operation, and it is a modulo operation. And here we have usual addition and product operation. The operation is different.
Yes.
Okay. Because here, suppose I consider Z4. In Z4, we have 0, 1, 2, 3. And if I add 2 plus 3, I'm not getting 5, which is not equal to 5, which is congruent to what? Tell me. 5 is congruent to 2. Yes or no?
Yes.
And in here, 2 plus 3, I am getting 5 because operation is simple 5. Operation matrix. And what I want the same operation. Then it is a. So here we have modulo operation. What? So
Yes.
operation is
Yes.
different. That's it.
Okay.
So now next, very interesting one. Then we will stop. A zero divisor. So what is definition of zero divisor? So let's see. Let R be commutative ring. Now you understand what is in my commutative ring. What is commutative ring? Yes. What is commutative ring?
A is equal to B.
commutative law holds. You can
It
simply
or
say that A which is not equal to 0 and belongs to R. So any non-zero number, if you take A is not equal to 0 and which is belongs to R, is called as zero divisor. Is called as zero divisor if there exists B such that which is also non-zero and which is also belongs to ring, commutative ring, which is also non-zero such that their product A dot B is equal to 0. So give me any example here. Give me. What is the meaning of that? The meaning of that is what? Suppose you have any ring which is commutative. Okay. So commutativity is called A dot B is equal to B dot A. So you have A is not equal to 0 and B is also not equal to 0. Both the members of R, but their product is 0. So do you have any ring like that? Do you have such an element or such a ring? So for example, suppose let I have considered Z4 with respect to plus and dot. Whether it is ring, yes or no?
Yes, it is.
It is also commutative ring.
Yes.
Now, can you find any two numbers here which are non-zero but their dot product is 0? Their product is 0. You can find out here 2 into 2. Tell me what is 2 into 2 here?
It is equal to 4, which is congruent to 0.
0. So 2 dot 2 is equal to 0 under multiplication modular 4. Yes or no? So whether
Yes.
here 2 is equal to 0, 2 is not equal to 0, which is belongs to Z4. And again 2,
Is
which
not
is not equal to 0 and belongs to Z4. Therefore here that 2 we can write down in that way is zero divisor. Is zero
So
divisor
if there
of,
were two different numbers,
no, you can take same also, no problem.
no,
Okay.
I'm asking that, like, if there were two different numbers, like if A and both of them were different, then what would have been the zero divisor?
Yeah, so that two both are this also is zero divisor, this also A also is zero divisor, B also zero divisor. So let's take another example. Okay, so I have Z6 plus dot. Okay, is also ring, is it commutative ring? So two you can take 2 into 3. What is 2 into 3? 0. Where 2 is not equal to 0 belongs to R, and G also which is not equal to 0 belongs to R. Then 2 and 3. So you can write down like, so you will understand the zero divisor. 2 and 3 are zero divisors. In Z6 plus dot. Got it? Got it? Because what you want here by the definition, for any non-zero number, you want another non-zero number such that their product is 0. Got it?
Yes, sir.
Anyone any doubts here? So do you have any example with infinite groups here or infinite group? Yes?
so from the
No. I'm not getting you. Your voice is breaking. Your voice is breaking. Okay. Okay. So everyone understand zero divisor? You can take any elements. Okay. Okay. So now why that zero divisor is important? Because our next definition is field. So what is meant by field and what is the relation between group, ring and field that we are going to discuss in the next lecture. So you just keep that thing in your mind. This is nothing but what the definition of zero divisor. So we want R be a commutative ring. Then you want two elements from R such that both are non-zero. If I do the product, we will get the product is zero. This is called as a zero divisor. Got it, everyone?
Sir, we did not explain that how 2.3 came as 0.
What is 2.3? Tell me.
Sir, because of 0 it is 0, right?
No, it is Z. We are dealing in what? Just write down the above statement. No, what we have written here, it is commutative ring. Z6 is commutative ring. Are you agree with this? It's because we have discussed here. See, ZM is commutative ring. Where? Yeah, here ZM. You can see. We have discussed for ZM. This is similarly for ZM is also commutative ring. Okay. So I just take it this. You can check it out also. This is commutative ring. So I am taking that 2 and 3 from Z6 and I am doing that product, modulo n product. So 2 into 3 it becomes 6 and under modulo 6 it is 0. Yes or no?
Yes.
Got it? Similarly, what I did here only. So where 2 is not equal to 0, 3 is not equal to 0, but both are belongs to ring. Ring is nothing but that Z6. Right now I'm talking about. Okay. And 2
Okay.
or 3 are the zero divisors. Got it now?
Yes.
Okay. So I request everyone please put your attendance in the chat box.